Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we're going to take a dive into section 3.7, derivatives of inverse functions. In this section, we will calculate the derivative of inverse functions and establish a formula for that. And we're also going to find the derivatives of the inverse trigonometric functions. Let's start with the idea of the derivative of an inverse. Now, if we take a look at the derivative, remember that that's the slope, and the slope is some sort of rise over run. So let's say we call a slope for the original function, we'll call it P or Q over P. Now, if we take a look at that point and how it's reflected with the inverse, reflected about the line y is equal to x, then you're essentially switching the x and y values. So instead of saying a f of a, you would have, or instead of saying a f of a, you would have f of a comma a, or you switch the x and y components. And since you are switching the x and y components, your slope therefore will also be the reciprocal. And so this is the relationship that they're trying to establish, is that if you want the derivative of an inverse at a particular point, it's really the derivative of the original function evaluated at the actual inverse place, but the reciprocal. So that's how the reciprocal plays in. One can look at it by setting y equals f inverse of x, and then saying x is equal to f of y, and then doing some differentiation there. So let's see how we can apply this inverse function theorem to finding the derivative of something that we haven't done yet quite. But we do have the derivative of the inverse of that function. So the function that I'm referring to here in this particular example is x to the 1/3. We know that its inverse function is x cubed, and so we can use that information to help us find this the derivative of this particular function. So what we're going to do is, let's just say g of x is equal to that cube root of x, x to the 1/3. And let's say that's the inverse of x cubed. So let's say your original function is x cubed. And so according to the inverse function theorem, the derivative of g is going to be 1 divided by the derivative of f evaluated at g of x. And so if we take the derivative of x cubed, that's going to be 3x squared. And then we're going to put in g of x, which is the cube root of x, in to that function that we just got, the derivative that we just got. And so we'll have 3 parentheses the cube root of x quantity squared, which is equivalent to 3 x to the 2/3. Now if we look at the cube root of x, that's x to the 1/3, and we have a 3, and then we have x to the 2/3. So there, it looks like there's something familiar that's happening there. And this is where we get to establish our power rule for rational exponents. So remember, we've had power rules for just positive integers, and then we saw the power rule for negative integers as well. And so now we're extending the power rule to cover rational exponents. So rational exponents are either some 1 over n, like 1/3, or in general it could be m over n, like we can now take the derivative of x to the 5/6, for example, and it's going to be the same thing because it's just going to be the power rule, except now we're applying it to other types of numbers. And so the derivative of x to the 1 over n is going to be 1 over n times x raised to the 1 over n minus 1. And I have to caution you that when you're subtracting 1 from a fraction, we have to keep in mind how that works. So and also this is also going to work for m over n as well. Okay. And finally, the other big thing in this big topic in this section is the derivative of the inverse trig function. And so the book talks about a way to find the derivative of the inverse function, but here's another way that kind of takes advantage of the chain rule. And this is actually a step ahead and would be covered in implicit differentiation. But let's just take a peek at how this process is done. So say we're looking for the derivative of the arc sine of x, and so arc sine of x should be some angle of something. Let's call that theta, so that sine of theta is equal to x, or sine of theta is equal to the sine of the arc sine of x, which is equal to x. And so that's because arc sine is the inverse of the sine. So the derivative of the sine function is the cosine function, but according to our chain rule, we have to make sure that when we're taking the derivative with respect to x, and theta is not x, it's a function that has an x in it, then we have to follow it up with a d theta dx. And the derivative of x is just 1. So from there, you get d theta dx, which is essentially what you're looking for, is equal to 1 over cosine theta. Now, the original problem did not have a theta in it. It had an arc sine of x. And so we have to somehow get our positions back to x's and not thetas. And so since theta is equal to arc sine of x, we can replace theta with arc sine of x, and the cosine of the arc sine of x here, in this case, we would use this triangle, this right triangle, and we get the cosine to be the square root of 1 minus x squared. And so if we piece that all together, we're going to get the derivative of the arc sine function to equal to 1 divided by the square root of 1 minus x squared. All right, so that's the derivative of the arc sine. You can similarly come up with a derivative of the arc cosine, arc tangent, and all those other arc functions, and then you're going to get a list of these derivatives, and here is the list of derivatives for the inverse trigonometric functions. All right, that's your overview of section 3.7. Good luck.